Welcome to all of my students. Today I will deliver lecture number 13. So today we start congruence relation. Before that, first I will tell you what is compatible relation. Definition. Let S be a semigroup a relation R on S is called left compatible. On S is called left, in bracket I will write right compatible. If for every S comma T comma A belongs to S comma T belongs to R, implies AS comma AT, in bracket I write SA comma TA belongs to R. Correct? Means S is a semigroup and R is a binary relation on a semigroup S. R is a binary relation on a semigroup S, means that R is the subset of S cross S. Correct? Now we say that R is left compatible if for every S comma T comma A belongs to S comma T belongs to R, implies AS comma AT belongs to R. And now if it is right compatible, then we say it is right compatible if SA comma TA belongs to R. That's why I write it in the bracket. Left compatible if AS comma AT belongs to R, and right compatible if SA comma TA belongs to R. Correct? And we say that a relation R on S is compatible if it is both right as well as left compatible relation. If R is both right as well as left compatible, then we say that it is called compatible relation. Or you can also just that is for every S comma T comma S dash comma T dash belonging to S comma T S dash comma T dash belonging to R, implies SS dash comma TT dash belongs to R. Correct? Just I combine both. Or also you can say that AS comma AT belongs to R and SA comma TA belongs to R. For every AST, it means that R is compatible because it is left as well as right compatible. Or also you can just equivalently you can write for every S comma T S dash comma T dash belongs to S comma T S dash comma T dash belongs to R, implies SS dash comma TT dash belongs to R. So if this condition holds, the single condition implies that R is what? Compatible relation. Means it is right as well as left both. Correct? So now think about the example. Now you see that if you take S as a right zero semigroup, correct? If you take S as a right zero semigroup and you take relation R as, for example, if S is like this, x1, x2, x3, x4, for example, this is the right zero semigroup, it is so. Then what happens? Then you have this thing xi, xj will be what? If it is right zero semigroup, it will be what? Xj. Correct? Now, if you consider any relation R, say any relation, if you consider see x2 comma x3, this is the relation. This is the relation on a semigroup, or is relation on semigroup S, which is what? It is left compatible or right compatible. You can see that for every A belongs to S, you can observe that AX2, AX3 will be what? If you calculate AX2 comma AX3, what will be the value of AX2? AX2, see, it is right zero semigroup, so it will come as X2, X3. So it goes in R. So it means what? This relation is what? This relation is right compatible relation, but not left compatible. Because you see, if you multiply by like this, x2a, x3a, for example, so it will come as a comma a, but which does not belongs to R. Because see, R is a relation what? X2 comma x3 is a relation. Here S is it could be a comma a means what? It could be anything, x1 comma x1, x2 comma x2, x3 comma x3, x4 comma x4. So this is not present here. So R is not left compatible. So if semigroup is right zero semigroup, the relation R on a right zero semigroup is right compatible. Or if you say, if you take S as left zero semigroup, correct? Then relation on left zero semigroup is left compatible. You can verify by yourself, compatible, all of you can verify left compatible, but not right. Correct? So this is the right zero semigroup xj, and you see that it is right compatible. If you see the definition, as comma at, when a is multiplied from the left, then it is what? When a is multiplied from the left side, then it is called left compatible. So ax2 comma ax3 is equal to what? x2 comma x3. So ax2 comma x3. So it is what? So it is left compatible, not right. Reverse are there, but not right. Now if we change now, if we take as left zero semigroup here, that is xi into xj is now xi, and R be same, x2 comma x3 is a relation on a semigroup, which is what? Now it will be right compatible, but not left, because when you multiply it from left, and as it is left zero semigroup, so ax2 will be what? It will be a, and a does not goes in R. Now if x2a comma x3a, so it will come as x2, x3, and now it goes in R. So this relation R is now right compatible, but it is not left compatible. So whenever the semigroup is right zero semigroup, R is left compatible, and when R is left zero semigroup, R is right compatible. So reverse action is there. Now we define congruence relation. a left in bracket I right a left compatible equivalence relation on a semigroup is called left and right congruence on S. See, if R is equivalence relation, first of all R should be equivalence relation. If R is equivalence relation and if R is left compatible, then we call it as left congruence. When R is right compatible, right compatible in equivalence relation, right compatible equivalence relation is called right congruence. Left compatible equivalence relation is called left congruence. And when it is both, I mean to see that when equivalence relation is compatible, then that compatible relation is called equivalence relation. So you can write just a compatible equivalence relation on a semigroup S is called congruence on S. A compatible equivalence relation on a semigroup S is called congruence on S, correct? Now what about the examples? The same example I take of semigroup, that you take either right zero semigroup, right, or you say left. You take any semigroup. Either you take right zero semigroup or you take left zero semigroup, correct? Now any equivalence relation, let R be any equivalence relation on S, correct? Then R is congruence on S. Basically what happens when R is reflexive relation, you take either right zero semigroup or left zero semigroup, that reflexive relation is a compatible relation, isn't it? See, in the previous example, if we take for example S as x1, x2, x3, x4, this is the example. For example, you take left zero semigroup, xi, xj is equal to xi, correct? So we have already seen if you have taken relation, for example, x1 comma x2. Now you take R such as one S is also contained in R. Now you take like this. So R is what? One S union, for example, you take any relation, x1 comma x2 you take, correct? And now R is what? That is, R is what? Reflexive. Now you see that R is compatible. See, for every A belongs to, you write like this, for every xi belongs to S, correct? Now if you calculate xi, x1, xi, x2, calculate this, and x1 into xi into x2 into xi, calculate both. So you see that as we have taken xi, xj is equal to xi, it means what? This is left zero semigroup, it will come as xi, correct? So it is left compatible, we have already seen. Now here you see x1 into xi, it come as x1, correct? And here it come as x2. We have taken a left zero semigroup, that is xi into xj is xi. So here xi x1 is what, xi x1 is what, xi x2 is what, xi. So xi comma xi will go where? R. It will go in R. Why? Because R is reflexive. So it means that this is left zero semigroup, correct? So left zero semigroup is also left compatible, and left zero semigroup is also right compatible. So such R is what? Compatible. Compatible. So it means what? It means that when R is a reflexive relation, then if you take right zero semigroup or left zero semigroup, then that relation will be compatible. Now if you are taking an equivalence relation here you are taking. So of course when relation is equivalence, it is reflexive. So this relation R is compatible on S. So being compatible equivalence relation, it is congruence on S. So then R is a congruence on S. R be an equivalence relation on S. Whether you take right or left, it doesn't matter. R will be congruence on S. Correct? So this is example. Now we do proposition 1.5.1. A relation rho on a semigroup S is a congruence if and only if it is both left and right congruence. So if you have to prove that if relation is congruence, then it is left congruence, and also it is right congruence. And now conversely, you have, if relation rho on a semigroup F if it is left congruence and right congruence, then you have to prove that it is a congruence. So basically, you have to verify the definition of both. That is proof. Let rho is congruence on semigroup S. Correct? Then what you have? Then for every A comma S comma, you see S comma T comma S dash comma T dash belongs to S. S comma T comma S dash comma T dash belongs to rho implies what? SS dash comma TT dash belongs to rho. This is by definition of the congruence, correct? Now you see you have to prove left congruence as well as right congruence, correct? So it means that for every A comma S comma T belonging to S, A comma A and S comma T belonging to rho, A comma A will go in rho. Why? Because rho is what? Rho is being congruence, it is equivalence. So being equivalence, it is reflexive. So A comma A naturally will go in rho, and we have taken S comma T in rho, correct? So it implies that AS comma AT belongs to rho. It implies what? Rho is what? Left compatible. It implies that rho is left congruence. Similarly, rho is right congruence. SA comma TA will go in rho, so it will be right congruence. Now see the converse part. Let rho is both left and right congruence, correct? Then what we have? We have to prove basically congruence, correct? To prove congruence, we have to prove that if for every s comma s dash comma t dash, s comma s dash comma t dash, s comma t dash belongs to rho implies s dash comma t dash. We have to prove this. What we have, this thing we have, that is, then for every a s t belonging to s comma t belongs to rho implies SA comma TA and AS comma AT both goes where? In rho. This we have, correct? Now for any s comma s dash comma t dash belongs to s, what we have? S comma t belongs to rho implies